Section: Introduction. In this section, we discuss reasoning language models, RLMs, like OpenAI's O1 and O3, and Alibaba's QWQ, which represent a significant advancement in AI, similar to the introduction of ChatGPT. These models enhance AI's ability to solve problems with better reasoning, contextual understanding, and decision-making across various fields. By building on standard large language models, LLMs, with advanced reasoning techniques, RLMs are becoming essential for achieving artificial general intelligence, AGI. However, the high costs and proprietary nature of these models, particularly those from OpenAI, create a gap between well-funded and less-funded AI systems, raising concerns about accessibility and fairness. Even QWQ, which is publicly available, lacks transparency regarding its training and data methods. This situation puts businesses and individuals who cannot afford these advanced systems at a disadvantage, potentially hindering innovation and perpetuating inequalities. As RLMs are increasingly used in critical areas like healthcare and science, it is crucial to address these disparities to ensure that the benefits of advanced reasoning are accessible to all. The technical aspects of RLMs are complex and not well understood, which adds to the accessibility issue. Current analyses suggest that RLMs likely incorporate techniques such as Monte Carlo tree search, reinforcement learning, process-based supervision, and advanced in-context learning methods. They also use various specialized components, including synthetic data generators and models for policy, value, and rewards, trained with innovative loss functions and fine-tuning methods. However, the detailed integration of these components into an effective system remains unclear. To tackle these challenges, we propose a comprehensive blueprint for building, analyzing, and experimenting with RLMs. This blueprint outlines the essential components of RLMs in a structured way, starting from a high-level overview down to specific implementation details. We present this blueprint from three perspectives: architecture diagrams, detailed formulations, and algorithm specifications, aiming to provide a clear guide for developing RLMs suited to different applications and constraints. Our blueprint includes various reasoning structures, such as chains, trees, and graphs, and supports different levels of reasoning, from individual tokens to full sentences. It also accommodates various training methods, including output-based supervision and process-based supervision. We introduce new schemes, like trace-based supervision, which enhances process-based supervision by using labeled paths through reasoning structures. We analyze existing reasoning methods to show how they fit into our blueprint, including standard designs like Monte Carlo tree search and reinforcement learning models, as well as innovative approaches like journey learning and advanced prompting techniques. By mapping these diverse methods to our framework, we demonstrate its versatility and ability to unify various reasoning strategies. To illustrate the practical application of our framework, we introduce X1, a user-friendly implementation that simplifies the development and testing of new RLM architectures. X1 supports various optimizations and scalability options, making it a solid foundation for experimentation. Our goal is to democratize access to advanced RLMs, allowing researchers and practitioners to design and deploy sophisticated models with less complexity and cost. Overall, our blueprint provides a flexible framework that encourages broader experimentation and innovation, while X1 serves as a platform for rapid prototyping and large-scale testing. By connecting theoretical advancements with practical applications, we aim to accelerate progress in the field and help reduce the gap between well-resourced and under-resourced AI systems. Section Summary. In this section, we introduce reasoning language models, RLMs, as a significant advancement in AI that enhances problem-solving and decision-making capabilities, while also addressing concerns about accessibility and equity due to their high costs. We propose a comprehensive blueprint for constructing and analyzing RLMs, offering a modular framework that supports various reasoning structures and training schemes, alongside a user-friendly implementation, X1, to democratize access and foster innovation in the field. Section: Evolution and Foundations of RLMs. In this section, we summarize the evolution and foundations of reasoning language models. We present an overview of their development history. The creation of reasoning-capable large language models, LLMs, stems from three key areas: advancements in LLMs like GPT-4, reinforcement learning, RL, designs such as AlphaZero, and high-performance computing, HPC, resources. Together, these elements have led to models that can perform efficient System 2 thinking, which involves thoughtful deliberation and innovative problem-solving, unlike the quick and automatic responses of System 1 thinking. We compare examples of these foundational pillars and discuss their details further. LLMs like GPT-4 and Llama represent significant progress in AI, serving as vast stores of knowledge embedded in their structure. Trained on extensive text from various sources, they can understand and generate human language fluently. However, their reasoning is mostly aligned with System 1 thinking, meaning it tends to be shallow and based on predicting the next likely word rather than engaging in deep problem solving. While they can produce convincing answers, these are often the result of statistical patterns rather than a thoughtful reasoning process. This highlights the need for integrating more advanced reasoning mechanisms into AI, leading to hybrid models that combine the knowledge of LLMs with structured reasoning techniques. Reinforcement learning has historically been a method for decision-making and exploration, allowing agents to learn optimal strategies through trial and error. Notable systems like AlphaZero have shown RL's potential by achieving superhuman performance in games like chess and Go without prior knowledge, learning entirely through self-play. One remarkable instance involved AlphaZero making a move initially seen as a mistake, which later turned out to be strategically brilliant, showcasing RL's ability to find unconventional solutions. However, traditional RL systems struggled with encoding real-world knowledge and complex reasoning tasks, prompting the integration of RL with LLMs to combine structured exploration with rich knowledge. The rise of LLMs and RL systems has been fueled by advancements in high-performance computing. Initially driven by Moore's law, which allowed for increased transistor density, HPC has evolved with technological improvements and cost-effective manufacturing. As miniaturization costs have surged, we have seen a shift towards parallelism and heterogeneous computing. Modern HPC systems utilize GPUs, TPUs, and AI accelerators for parallel tasks, alongside CPUs for general purposes. This heterogeneous approach optimizes performance, while distributed frameworks enable the training of large models across many computing nodes. Innovations in energy efficiency, such as sparsity and quantization, help manage the energy demands of scaling AI systems. These advancements ensure that HPC remains essential for developing AI models, supporting the integration of extensive knowledge, reasoning capabilities, and computational scalability. The convergence of LLMs, RL, and HPC has led to the development of models capable of System 2 thinking. These advanced systems merge the knowledge-rich foundation of LLMs with the exploratory strengths of RL, all backed by the scalability of modern HPC. The outcome is a new class of AI models that can engage in explicit and deliberate reasoning, equipped with a world model that allows them to analyze complex scenarios. Their combined capabilities enable them to explore vast decision spaces, assess various strategies, and refine solutions iteratively. Section Summary. In this section, we summarize the evolution of reasoning language models, RLMs, highlighting their development through the integration of large language models, LLMs, like GPT-4, reinforcement learning, RL, techniques exemplified by AlphaZero, and advancements in high-performance computing, HPC. This convergence enables RLMs to perform explicit, deliberate reasoning, System 2 thinking, while leveraging the vast knowledge encoded in LLMs and the exploratory capabilities of RL, thus paving the way for more sophisticated AI systems. Section: Interpolation, LLMs, versus Extrapolation, RLMs. In this section, we explore the differences between interpolation in large language models, LLMs, and extrapolation in reasoning language models, RLMs. Standard LLMs use a method that predicts the next token based on previous ones, which allows them to generate responses that fit patterns from their training data. However, This means they can only produce outputs that stay within the limits of what they have learned. On the other hand, RLMs can go beyond these limits. They use structured exploration to find new solutions and insights that are not confined to their training data, allowing them to engage in active problem-solving rather than just completing patterns. We also discuss the hierarchy of reasoning-related models. The development of RLMs shows a progression where earlier models, like GPT-4o, are less capable of reasoning, while newer architectures, like O1-like models, show more advanced reasoning abilities. This hierarchy reflects the combination of intuitive thinking, LLMs, and analytical thinking, RLMs. RLMs can be categorized into implicit and explicit reasoning models. Implicit models, like QWQ, have reasoning embedded in their structure and operate as black boxes, making their reasoning processes unclear. In contrast, explicit reasoning models, such as Llama Berry and Marco O1, have clear reasoning mechanisms that allow them to simulate and refine solutions, providing more flexibility and interpretability. Next, we describe the general architecture of RLMs, which we summarize in a figure. We outline the foundational architecture, operational pipelines, and core concepts. The RLM architecture consists of three main pipelines: inference, training, and data generation. The inference pipeline responds to user requests using models from the training pipeline. The data generation pipeline operates independently, creating data for retraining models, similar to the self-learning approach of AlphaZero. The inference process starts when a user provides a prompt, which outlines the problem to be solved. This prompt initiates a reasoning structure, typically represented as a tree, where the root corresponds to the user's input. As we explore potential solutions, we generate nodes that represent reasoning steps, which are coherent units of thought that either explore new areas or build on existing ideas. The reasoning structure evolves through a method inspired by AlphaZero, using policy and value models to guide the search for solutions. The policy model generates new reasoning steps, while the value model assesses the quality of reasoning paths. The process continues until we reach a terminal step, which concludes the reasoning chain and provides the final answer. This architecture allows us to handle a variety of reasoning tasks, adapting to both detailed and broader reasoning steps. By structuring the search space and guiding exploration, RLMs bridge the gap between intuitive pattern recognition and deliberate problem solving. Further details on the inference pipeline can be found in the appendix and algorithm sections. Section Summary. In this section, we differentiate between interpolation in standard LLMs, which generate outputs based on training data patterns, and extrapolation in reasoning LMs, RLMs, which explore beyond these boundaries to solve problems creatively. We also outline the hierarchical evolution of RLMs, distinguishing between implicit models that operate as black boxes and explicit models that incorporate external reasoning mechanisms, ultimately describing the architecture and processes involved in RLMs' inference and training pipelines. Section: Training. In this section, we outline the training process for our models, which varies based on the type of model being trained, such as value, policy, or reward models. Generally, we focus on fine-tuning a model like Llama. Our approach begins with using supervised data from existing datasets, such as PRM800K, which forms part of the supervised training data in our training pipeline. Next, we implement an unsupervised training pipeline, where we continuously generate data to enhance the models. This data can come from inference, provided we maintain quality control, or from a synthetic data generation process that mimics inference. To gather this data, we run the RLM pipeline for specific tasks and collect the results. Depending on our collection method, the data may include only output-based labels, process-based labels, or trace-based labels that provide additional information about the operations used during the task-solving process. All this data is stored in a replay buffer for use in the unsupervised training scheme or to train a model that functions as an implicit RLM. We provide detailed specifications of the training pipelines in the appendix. We also recognize that our design can apply to various RLM architectures, even those that do not fully align with our framework. For instance, in some designs, a single node in the MCTS tree may represent an entire reasoning structure, focusing on transitioning between reasoning chains instead of individual steps. Our blueprint accommodates this through the concept of nesting, allowing a node to contain another reasoning structure. Other architectures, like journey learning, introduce unique elements, such as a transformation step that consolidates multiple paths into a new form for further reasoning. Despite these differences, our blueprint is flexible enough to include all these variations. Furthermore, integrating RLMs into broader LLM agent ecosystems allows for dynamic interactions with external tools and resources during execution. This can happen within the inference or data generation pipeline, where value or policy models enhance reasoning through retrieval-augmented generation, web queries, and specialized tools. For example, during reasoning tasks, models can query databases to verify steps or gather additional context, improving accuracy. This integration also supports adaptive reasoning, where the policy model can choose to invoke external functions to enhance decision-making. Additionally, it enables iterative improvements, allowing models to refine flawed reasoning paths by interacting with external validators. This framework aligns with scalable execution systems, facilitating access to cloud resources and ensuring robust performance in complex applications. Finally, we present our RLM blueprint, which serves as a foundation for developing new reasoning models and for analyzing and comparing different designs. The blueprint includes a toolbox of components for building RLMs, such as a reasoning scheme that defines the structure and strategy for solving tasks, a set of operators that evolve the reasoning structure, and pipelines that orchestrate interactions between these components for training, inference, or data generation. Thus, an RLM is defined as a combination of a reasoning scheme, operators, and associated models, along with the necessary pipelines. Section Summary. In this section, we outline our training framework for reasoning language models, RLMs, which combines supervised fine-tuning using existing datasets and an unsupervised self-learning pipeline that continuously generates data for model improvement. We also introduce our RLM blueprint, detailing its components, reasoning schemes, operators, and pipelines that facilitate the development and evaluation of diverse RLM architectures while enabling integration with broader LLM ecosystems for enhanced reasoning capabilities. Section: Reasoning Scheme. In this section, we discuss the reasoning scheme, which outlines the specific steps we take to reach a solution and how these steps connect to form coherent reasoning structures. A reasoning step is a basic unit that moves us closer to the solution, varying in length from a single token to larger text segments, depending on our design choices. Typically, we view a reasoning step as a complete thought, similar to a logical argument in a mathematical proof. This flexibility allows us to adapt to different problem areas, balancing detailed and broader reasoning approaches. We can use coarse steps, like logical arguments, to simplify our training data and improve interpretability, while single token steps help us incorporate uncertainty and advanced decoding methods into our reasoning model. However, finer reasoning steps can lead to more detailed exploration but also increase computational demands, especially when combined with search algorithms. The reasoning structure defines how our reasoning steps are organized. Common structures include chains, where each step follows the last, trees, which branch into multiple paths, and graphs, allowing arbitrary connections. Chains are often used in models based on the chain of thought approach, while trees are common in Monte Carlo tree search frameworks, enabling exploration of various paths. Graph structures allow for more complex dependencies, and we can also use nested structures for multi-step tasks. Our reasoning strategy dictates how the reasoning structure develops, detailing how we add and integrate new steps. Examples include Monte Carlo tree search, which balances exploration and exploitation, and beam search, which keeps a limited number of top options at each step. Ensemble methods combine different reasoning strategies to improve robustness and accuracy. We also differentiate between reasoning strategies and token-level decoding strategies. While decoding strategies generate token sequences, reasoning strategies focus on the higher-level integration of reasoning steps. Operators are tools we use to modify the reasoning structure. Structure operators can add or refine reasoning steps, enhancing clarity and coherence. For instance, the generate operator adds new steps, while the refine operator improves existing ones by addressing ambiguities or errors. We can also aggregate steps for coherence, prune irrelevant ones, and restructure the reasoning framework for better flow. Diversity in outcomes from our operators is important, as we want our generated reasoning steps to be distinct. We can achieve this through various methods, such as adjusting the temperature in our policy model or using diverse beam search. In Monte Carlo tree search, we can manipulate the balance between exploring new branches and expanding existing ones to enhance diversity. The reasoning space is vast, encompassing all possible token combinations, which grows exponentially with the number of tokens and vocabulary size. This makes exhaustive exploration impractical, so ensuring diversity in our exploration is crucial to cover the reasoning space effectively and avoid missing valuable paths. Section Summary. In this section, we describe the reasoning scheme as a structured approach that outlines the interconnected reasoning steps leading to a solution, emphasizing the flexibility in defining these steps to adapt to various problem domains. We also discuss the organization of these steps into chains, trees, or graphs, and the importance of diverse reasoning strategies and operators that enhance the reasoning process while managing computational efficiency. Section: Traversal operators. In this section, we discuss traversal operators, which guide our reasoning process through the existing reasoning structure. These operators are essential for determining the paths we take. The select operator helps us choose which reasoning steps to explore further. It assesses existing elements based on set criteria, like heuristic scores or performance metrics, to identify the most promising options. By balancing exploration of new alternatives and exploitation of known high-potential paths, we optimize our reasoning and resource allocation. The backtrack operator allows us to return to a previous reasoning step and pursue a different path. This is useful for correcting errors and revising hypotheses by moving away from unproductive directions. We can think of an additional backtracking generator as one that revisits earlier thoughts to explore new directions, illustrating how our QWQ model utilizes various generating transformations. The update operator improves specific parts of our reasoning structure without changing the overall framework. For instance, during the backpropagation phase in Monte Carlo tree search, MCTS, we update evaluation scores along existing steps to guide future decisions. We can also refine the content of individual nodes, replacing them with better versions, including refining the initial prompt even if it wasn't generated by our policy model. Evaluate operators assess segments of the reasoning structure and provide values without altering the structure. They are often used in reasoning strategies like MCTS. A key evaluation occurs when we reach a terminal state, allowing us to check if the final step leads to a correct solution, especially in tasks with clear answers. We can also evaluate intermediate steps by estimating rewards or using trained models for efficient assessments. Selecting the right metrics for evaluation is crucial. We must differentiate between the decoding strategy for generating token sequences and the structure operator that adds reasoning steps to the overall framework. Decoding strategies, such as greedy decoding or beam search, operate at the token level, while structure operators function at the reasoning step level. Models implement various operators, with the value model handling evaluations and the policy model managing generation. Each model requires training according to a specific paradigm, which outlines how we optimize performance. This includes defining the loss function and data procedures. Training schemes for reasoning tasks have evolved from early work like AlphaZero to support the complexities of large language models, LLMs. Common paradigms include supervised fine-tuning, rejection sampling, and reinforcement learning methods like proximal policy optimization and reasoning policy optimization. Some paradigms also involve self-learning, where the model improves by generating and evaluating its own reasoning sequences. Section Summary. In this section, we describe traversal operators that guide the reasoning process by selecting, backtracking, updating, and evaluating reasoning steps within a structure. We also discuss the importance of distinguishing between decoding strategies and structure operators, as well as the various training paradigms used to optimize model performance in reasoning tasks. Section: Training Data Scope. In this section, we discuss the training data used for reasoning language models, RLMs, and how it can differ in capturing reasoning structures. We present two main approaches: output-based supervision, OBS, and process-based supervision, PBS. More details about these methods can be found in the appendix. In OBS, each training sample includes just the input and the final output, like a math problem with its solution marked as correct or incorrect. This method is easy to implement and collect data for, but it may limit the model's reasoning accuracy since it lacks information about the steps taken to reach the solution. On the other hand, PBS provides a more comprehensive training sample that includes the input, final output, and all intermediate reasoning steps, each labeled for quality. This richer data helps the model learn detailed reasoning patterns, enhancing its ability to produce accurate and understandable solutions. However, gathering this type of data is more challenging. By adjusting the training data scope, we can balance the ease of data collection with the depth of reasoning insights. Generally, dense supervision leads to better performance but requires more complex data. We also mention trace-based supervision, TBS, which could enhance PBS by detailing the sequence of reasoning steps, helping the model learn not just the steps but also how to navigate the reasoning process effectively. Next, we define a pipeline as a set of operations that coordinates the interaction between the reasoning scheme and the models to achieve specific goals. Typically, an RLM has one pipeline for inference and another for training, along with possible pipelines for generating synthetic training data. We differentiate between pipelines for training implicit RLMs using reasoning traces and those for explicit RLMs. The specifics of these pipelines depend on design choices, which we describe in detail in the appendix. We also discuss optimizing the verifier, which selects the best answer from a set of proposals. The standard method is best of n sampling, where we choose the best solution from n samples. However, we can enhance this by using a process-based verifier or a process reward model, PRM, that evaluates the correctness of each reasoning step, allowing for a more efficient search for solutions. Finally, we illustrate how our framework can model various existing RLMs and related works, summarizing our findings in a table. We start with common explicit RLM architectures based on Monte Carlo tree search, MCTS, and policy or value models, where each reasoning step is a logical argument. We also explore designs that generalize this approach and examine implicit RLMs and structured prompting schemes, demonstrating their compatibility with our framework. Section Summary. In this section, we discuss two approaches to training data for reasoning language models: output-based supervision, OBS, which provides minimal insight into intermediate reasoning steps, and process-based supervision, PBS, which includes detailed reasoning structures for improved accuracy. We also introduce trace-based supervision, TBS, as a way to enhance PBS by capturing the full sequence of reasoning steps, and we outline the role of pipelines in orchestrating model training and inference processes. Section: Explicit RLMs. In this section, we discuss explicit reasoning models, RLMs, starting with the most common types that follow the architecture we outlined earlier. These models, like TSLLM, Alpha LLM, and MCTSDPO, typically use a tree structure where each node represents a unique reasoning step. Their reasoning strategy is based on Monte Carlo tree search, MCTS, focusing on exploring, expanding, and evaluating nodes iteratively. By using value mechanisms, such as prompt-based evaluations, the system can identify and prioritize the most promising branches, leading to better decision-making and refinement of the reasoning process. All MCTS-based models include at least three operators: one for generating the next step, one for evaluating, and one for updating values. Some models, like REST MCTS, Llama Berry, and Marco 01, also include a refinement operator to enhance reasoning steps. Journey learning differs from typical MCTS-based RLMs in two key ways. First, it uses a linearization structure operator, transforming the tree into a chain by combining selected reasoning chains into a single long chain. This approach allows it to draw insights from various branches while maintaining a simple linear reasoning structure that supports self-correction and exploration of multiple hypotheses. Second, journey learning has a pipeline for internalizing these long reasoning chains into its weights, enabling the model to generate them directly from its weights, making it an implicit RLM. This transformation allows the model to adopt a more fluid reasoning approach over time, introducing a backtracking generator function. As a result, the trained RLM has an implicit chain reasoning structure, generating new steps in the chain by leveraging different generators. It can either continue along the current path or backtrack to explore alternative solutions, revising its reasoning output until it finds the best result, all while maintaining a chain-based structure. Next, we look at implicit RLMs, such as QWQ, which features a fully implicit reasoning model. In QWQ, the reasoning structure is generated auto-regressively from the model's weights. The reasoning strategy involves generating the next step, backtracking, summarizing, and critiquing to arrive at the final solution. At each step, the model creates a new node in the chain using one of these four implicit generation operators. We also highlight advanced structured prompting schemes like COT, TOT, and GOT, which represent fully explicit RLM structures without any implicit reasoning beyond what is provided by the underlying language model. COT uses a chain of reasoning steps to construct a coherent solution, requiring only a generation operator. It serves as a foundation for various advanced reasoning strategies, including self-consistency and self-refinement. Self-consistency adds redundancy by generating multiple reasoning chains and using majority voting to find the most consistent solution. TOT organizes reasoning in a hierarchical tree structure, where each node represents a distinct step, allowing exploration of multiple pathways. GOT employs a more complex graph-based representation, where nodes represent reasoning steps, and an external controller guides the exploration and refinement of the graph. Finally, we explain how to use our blueprint for applications in a tutorial style. The first step is to define the reasoning scheme, which outlines the foundational structure and strategy of the RLM. We begin by selecting the reasoning structure. Chains are cost-effective, trees are more expensive but offer rich branching, and graphs provide flexibility but can be challenging to implement. Next, we decide on the granularity of reasoning steps, choosing between coarse-grained steps for simplicity or token-based granularity for precision, which requires more resources. We also select a reasoning strategy to guide the evolution of the structure, with MCTS being the most common due to its balance of exploration and exploitation. Finally, we determine the specifics of our chosen strategy, including parameters that will significantly influence the model's reasoning dynamics and effectiveness. Each decision at this stage is crucial for tailoring the RLM to meet our specific application needs. Section Summary. In this section, we explore various reasoning models, RLMs, distinguishing between explicit models like TSLLM and journey learning, which utilize tree structures and iterative exploration, and implicit models like QWQ, which generate reasoning chains auto-regressively. We also discuss structured prompting schemes such as COT, TOT, and GOT, highlighting their unique approaches to reasoning and the importance of defining the reasoning scheme and strategy for effective application. Section. Part 2. Define the operators. In this section, we define the operators that will guide our reasoning process. For a design based on Monte Carlo tree search, MCTS, we start with the essential operators: generate, select, and backpropagate. These basic operations are sufficient for many situations and provide a clear framework for reasoning. We may also consider adding less common operators, like backtrack, which can help us track our progress in the search tree and refine earlier reasoning steps. This inclusion can enhance advanced training methods, such as trace-based supervision, by producing more detailed and structured data. Next, we need to decide how to implement each operator. We should determine which operators will use neural models, like a policy model for selection or a value model for backpropagation, and which will use traditional methods. This decision impacts the system's complexity and flexibility, so we must align it with our reasoning strategy and performance objectives. Moving on to training details, we outline how we will train the models that implement our operators. For our MCTS design, we typically use the policy model for generate and the value model for simulate. If needed, we can train a separate model to assess rewards at individual nodes, improving the accuracy of our reward signals. We must identify our application domain to ensure our models are trained on relevant data. We will define our models, including their architectures and base models, ensuring they fit our reasoning structure and goals. For training data, we can generate policy model data automatically using our pipeline or techniques like chain-of-thought prompting, including a special token for clear segmentation. For the value model, we will use full MCTS simulations to gather rich information about reasoning paths and outcomes. We will fine-tune our models as necessary. If we use coarse reasoning steps, we will perform supervised fine-tuning on the policy model to teach it step-by-step reasoning. We will do the same for the value model to establish it as a reliable evaluator. After initializing our models, we will run MCTS to collect additional data, filtering for high-quality reasoning paths or strong signals for further training. Finally, we will train both models using additional rounds of supervised fine-tuning or reinforcement learning methods like proximal policy optimization to ensure they are optimized for accuracy, efficiency, and robustness in complex reasoning tasks. We will also define our reasoning instance space, which includes our action and state space, and establish a reward structure that fully defines our Markov decision process. We recommend using an MCTS variant and extending it to address speed, exploration, quality, and supervision concerns. This may involve adding refinements, model supervision similar to AlphaZero, and exploring options like entropy-infused PUCT or non-greedy expansion. In our framework, we will employ a tree reasoning structure alongside MCTS as our reasoning strategy. This combination allows us to systematically explore reasoning paths while balancing the exploration of new options and the exploitation of promising solutions, guided by a value model. We achieve this through a series of operators that help us construct, traverse, evaluate, and update our reasoning tree. Section Summary. In this section, we define the core operators for our MCTS-based reasoning framework, including generate, select, and backpropagate, while considering the potential addition of operators like backtrack for enhanced tracking and training. We also outline the training specifics for our models, emphasizing the importance of aligning model architectures and training data with our reasoning objectives to optimize performance in complex tasks. Section: Operators. In this section, we describe the operators used in our reasoning framework. The generate operator is essential for expanding the reasoning tree by adding new child nodes to a chosen node. To enhance the diversity of these nodes, we utilize diverse beam search, which promotes variability among the generated children. Alternatively, we can apply high-temperature sampling to introduce randomness into the generation process, encouraging the exploration of various reasoning paths. We manage the traversal of the reasoning tree with the select operator, which employs the PUCT function to determine the next node to expand. This operator strikes a balance between exploring less visited nodes and exploiting nodes that have shown higher potential based on prior evaluations. Starting from the root node, this traversal mechanism allows us to dynamically explore different paths and recover from less optimal choices by backtracking and selecting new branches. The backpropagation update operator refines the Q values, which guide the select operator along the path from an expanded node back to the root. This process integrates new information from downstream nodes, leading to increasingly accurate Q values for intermediate nodes. These refined Q values inform our future decisions, enhancing the robustness of the reasoning process over time. We implement two evaluate operators. The first, the reasoning path evaluation operator, predicts the expected future reward for a path from the root to a specific node, based on the Q-value model. The second, the ground truth-based reward operator, evaluates leaf nodes for correctness when the actual answer is known, assigning fixed rewards to verified solutions. These rewards are then incorporated into the Q-values of upstream nodes, ensuring that our reasoning process is informed by both model predictions and objective validation. Regarding our models and training paradigms, both the value and policy models are fine-tuned versions of a large language model, LLM, without relying on prompting, which is common in other architectures. This design choice aims to enhance the quality of our results. For training the policy model, we use the LLM to generate new nodes during Monte Carlo tree search, MCTS. It is fine-tuned to produce individual reasoning steps rather than complete chains of thought. We introduce a new token, the end of intermediate step, EWA, token, to signify the completion of each reasoning step, complementing the standard end of sequence, EOS, token. This dual token approach allows us to clearly identify intermediate reasoning steps, improving interpretability and ensuring the model recognizes when a solution is reached. In training the value model, we adopt terminology from reinforcement learning to clarify the motivation behind Q-value models. The MCTS tree consists of nodes and edges, where a path represents a trajectory with nodes as states and edges as actions. Each node contains a chain of reasoning steps, and an action corresponds to adding a new step. The value model evaluates whether a proposed reasoning step should be added, estimating the future value of this addition. The Q-value model predicts the expected discounted future rewards for a sequence of reasoning steps when adding a new step. We define the Q-value for traversing an edge to a new node as the expected reward discounted by the number of steps needed to achieve it. The terminal state is where no further reasoning steps can be added, typically representing the final solution to the problem. We model rewards as sparse, meaning only the last reasoning step receives a non-zero reward, as only the final answer can be evaluated against the true solution. We approximate the Q-value by sampling reasoning chains until reaching the terminal state and averaging the terminal rewards, discounted by the depth required. The Q-value model is trained using data from completed MCTS searches. Initially, when the Q-value model is not available, we perform simulations and use the average discounted reward to initialize the Q-values for each node. More details can be found in the appendix. Section Summary. In this section, we describe our reasoning framework that utilizes operators like generate, select, and backpropagation update to dynamically expand a reasoning tree and refine Q-values for improved decision-making. We also detail our training approach for both the policy and value models, emphasizing the use of a novel EWA token for intermediate reasoning steps and a sparse reward structure to evaluate reasoning chains effectively. Section: Enabling Scalability and Efficiency. In this section, we discuss how we enable scalability and efficiency in our implementation, which is designed to work across multiple GPUs and nodes. To improve scalability and computational efficiency, we have made several architectural and operational enhancements. One key change is the separation of the value and policy models, allowing us to deploy dedicated value and policy servers. This separation offers several benefits. 1. Scalability. By decoupling the value and policy servers from the MCTS instance, we can run multiple parallel MCTS instances more easily. 2. Batch processing. The policy server can handle multiple queries at once, increasing throughput. 3. Resource optimization. Our framework's architecture allows us to allocate computational resources independently to the value and policy models, leading to better resource use. 4. Replication and distribution. The separation allows us to apply different strategies for replicating and distributing these models. We illustrate this server architecture in a figure, showing how these improvements enhance scalability and efficiency. Building on these enhancements, we implement strategies to optimize efficiency and scalability, particularly in inference and parallelization. We use standard optimizations like batching, quantization, and KV caching. In the policy model, we batch inference calls to process multiple queries simultaneously. During node expansion, we create multiple child nodes in parallel, generating 84 new nodes at each step, which reduces computational load and boosts performance. We also speed up inference through KV caching, which reduces redundant calculations, and quantization, which lowers memory usage for both models. Next, we analyze strategies for generating and selecting detailed token-based reasoning steps. We use metrics like variance, entropy, var entropy, and the Gini coefficient to examine the token probability distribution. Variance indicates uncertainty. Low variance suggests a flat distribution. Entropy measures uncertainty in a distribution, with high entropy indicating a need for more information to describe the system. Var entropy measures changes in entropy, where high var entropy and low entropy suggest few probable outcomes, while low var entropy and high entropy indicate a flatter distribution. The Gini coefficient measures inequality, with a value of 0 representing perfect equality and a value close to 1 indicating high inequality. We present visualizations of token probabilities, allowing us to assess the distribution based on the highest and second highest probabilities. We identify scenarios where the top two probabilities are close, suggesting that forking in the sampling process could be advantageous. We also note instances of high confidence and high uncertainty, where correcting previous errors might be more beneficial than forking. Our analysis shows that the zero-shot prompt appears less uncertain, likely leading to better outputs. We also observe high uncertainty around certain tokens, indicating prediction challenges. Most words are represented by single tokens, suggesting that the next token is likely evenly distributed across the English language. Low uncertainty indicates high confidence in predicting the next token based on context. These uncertainty values reflect learned statistical patterns rather than the actual language structure. Finally, we explore how to use these metrics, particularly combining entropy and var entropy, to inform our reasoning strategy. High var entropy and low entropy suggest that a tree search could be useful, while low var entropy and high entropy indicate a need for clarification, as all outcomes are equally unlikely. We find that these metrics often highlight tokens that, while not essential for the task, are important for design and formatting decisions. Section Summary. In this section, we describe our framework's architectural improvements that enhance scalability and efficiency by decoupling value and policy models, enabling batch processing, and optimizing resource allocation. We also analyze token-based reasoning using metrics like variance, entropy, and Gini coefficient to assess uncertainty and inform our reasoning strategies. Section: Further improvements. In this section, we explore several strategies for enhancing our policy model's performance and scalability. First, we recognize that scaling the replication and distribution of our model across multiple GPUs or compute nodes can lead to significant improvements, especially for large models. We also consider dynamic batching techniques, such as replacing completed sequences with new inputs or grouping similar token sequences, to boost processing speed and efficiency. Next, we propose using a unified trunk architecture for both the policy and value models, which would eliminate the need for a separate value server. This change would simplify model calls and reduce the time needed for initialization. Additionally, we look at speculative decoding methods that could speed up inference by using intermediate results for predictions while the full calculations are still underway. We also suggest implementing selective rollouts, where we only evaluate terminal nodes if their Q value exceeds a certain threshold, optimizing our evaluation process. Moving on to effective reinforcement learning models, we emphasize the importance of using a dedicated value model. This model provides a stable evaluation framework, especially in complex reasoning tasks, allowing us to better control the quality of our outputs. We advocate for process-based evaluation, which assesses the entire reasoning structure rather than just the outcomes. This method has proven to yield more reliable results and helps refine our model's reasoning paths. Adopting a two-phase training strategy is another key recommendation. By first establishing a solid foundation of reasoning patterns and then fine-tuning under more complex conditions, we can enhance our model's performance and stability. Training on familiar data distributions is crucial as well. It helps our models internalize essential reasoning patterns before tackling more challenging tasks, ensuring better initial performance. We also caution against relying solely on prompting large language models to critique their outputs, as this often leads to instability. Instead, we find that structured training approaches yield better self-improvement capabilities. In summary, we believe that by implementing these strategies, such as using dedicated value models, process-based evaluations, two-phase training, and familiar distributions, we can significantly enhance the robustness and effectiveness of our reasoning models. Section Summary. In this section, we outline strategies for enhancing the scalability and efficiency of reinforcement learning models, including the use of dedicated value models, process-based evaluations, and a two-phase training approach to improve reasoning capabilities. We emphasize the importance of training on familiar data distributions to maintain model stability and performance, while cautioning against relying solely on prompting for self-evaluation, which can lead to inconsistent results. Section: Benchmarking. In this section, we provide an overview of different types of reasoning and highlight benchmarks for each category. For mathematical reasoning, we note that benchmarks include tasks in arithmetic, geometry, and other areas that rely on logical thinking and symbolic computation. These benchmarks can be divided into those with fixed datasets and those based on templates. For example, GSM-8K has a training set of 7,473 samples and a test set of 1,319 samples, featuring grade school level math word problems. Language models made significant progress by training on this dataset. GSM Symbolic uses 100 templated questions from GSM-8K to show the limited generalization of current models and the importance of templates in evaluating their performance. The math benchmark includes 12,500 problems of varying difficulty, sourced from math competitions, with 7,500 for training and 5,000 for testing. Functional math builds on this by introducing templates to assess understanding of math concepts, though its resources are not publicly available. Other benchmarks like AMY, AMC, and Gaokao cover a range of difficulties, with AMY being the most challenging. Olympiad Bench includes 8,476 problems from international competitions, while College Math focuses on college-level math with 1,281 training and 2,818 test problems. UMath features 880 university-level problems, and Frontier Math presents expert-level challenges, with less than 2% of these problems solvable by current models, indicating a gap between AI and human expertise. We recommend using templated benchmarks to avoid contamination from prior training exposure, providing a clearer measure of performance. In logical reasoning, we emphasize formal processes like propositional logic and automated theorem proving. Pronto QA generates ontology graphs to create statements and questions that require logical reasoning. The abstract nature of these graphs pushes models to rely on step-by-step reasoning rather than common-sense inference. Big Bench is a large benchmark with over 200 tasks across various domains, using templated questions for systematic evaluation. The ARC challenge tests understanding of formal patterns and logical structures in grid-based tasks. For causal reasoning, we focus on understanding cause-effect relationships. The Tübingen cause-effect pairs dataset includes 108 pairs from various fields, serving as a benchmark for causal reasoning. The neuropathic pain dataset examines complex relationships between nerve function and symptoms, requiring specific knowledge for accurate interpretation. The Arctic sea ice dataset models dynamics of sea ice using satellite data, allowing exploration of causal relationships in climate systems. The CRAS benchmark assesses counterfactual reasoning with 274 multiple-choice questions, measuring models' abilities to answer these questions. However, many of these benchmarks have been largely solved or are not suitable for current models, limiting their effectiveness in real-world applications. Section Summary. In this section, we distinguish between various reasoning types, mathematical, logical, and causal, and present benchmarks for each, highlighting their unique characteristics and challenges. We emphasize the importance of templated benchmarks for evaluating language models' performance, particularly in mathematical reasoning, where current models still struggle significantly compared to human expertise. Section: Common Sense Reasoning. In this section, we discuss common sense reasoning, which involves tasks that require everyday knowledge and understanding of cultural, social, or contextual factors. This includes specialized knowledge in fields like chemistry, genetics, biology, and physics, as seen in the GPQA benchmark, which features 198 questions designed for experts in their fields but challenging for those outside them. MMLU, STEM, includes a range of questions from general common sense to specialized knowledge. When benchmarking reasoning language models, RLMs, we note that using multiple models can increase output variability. Therefore, we stress the need for large sample sizes to ensure fair comparisons. Benchmarks like AMI or AMC, which have only a few samples, risk selective reporting. Our findings suggest that to achieve low error variability, we need to evaluate over 500 samples, and we recommend at least 200 samples per benchmark and a minimum of 500 samples per category for reliable performance comparisons. We also highlight that while RLMs have been studied from various perspectives, there are still gaps in providing a systematic framework for their development. We categorize previous efforts and explain how our work contributes to the field. Several studies have focused on improving the reasoning abilities of standard LLMs through techniques applied during pre-training, fine-tuning, or inference. For instance, Huang and Chang discuss pre-training on reasoning datasets, while Sun et al. Introduce alignment training and mixture of experts architectures. Huang et al. Show that self-improvement is possible with additional training on self-generated labels. Chao et al. Classify prompting techniques into strategy-enhanced and knowledge-enhanced reasoning, while Besta et al. Outline advanced in-context reasoning methods like chain of thought and tree of thoughts. However, many of these studies mainly review existing literature without providing code or covering explicit reasoning models. Our blueprint aims to integrate these techniques into a comprehensive framework. We also explore explicit reasoning models that go beyond basic pre-training methods. These involve additional computations to refine reasoning paths, which can increase training and inference demands. Dong et al. Categorize self-improvement methods, while Guan et al. Propose a three-stage verifier engineering process to enhance model outputs. Zhang et al. Offer a roadmap for reproducing OpenAI's reasoning model but do not provide implementation details. Our summary includes various specific RLM implementations, and we present a foundational framework that is broadly applicable. Lastly, we address the design of scaling test time compute, TTC, with Chen et al., analyzing the balance between token usage for simpler problems and the need for exploration in more complex tasks.